Alright, welcome to the final problem for the Tempo Project 3. This is problem 2, and this video will conclude the Thermodynamics ePortfolio Tempo project for the summer of 2014 for ME 302. Let's get started. So, this problem states, an air standard cycle is executed in a closed system with 0.004 kilograms of air and consists of the following three processes. Step 1 to 2, isentropic compression from 100 kPa and 27 degrees Celsius to 1 MPa. 2 to 3, constant pressure heat addition in the amount of 2.76 kilojoules. 3 to 1, pressure is equal to constant 1 times V plus constant 2 heat rejection to initial state. C1 and C2 are constants. A, show the cycle on PV and TS diagrams. B, calculate the heat rejected. C, determine the thermal efficiency. Assume constant specific heats at room temperature. Alright, so the first step, A, is going to be to draw our PV and our TS diagrams. Okay, so they gave it to us as the first step. We're going to draw it as the first step. The first step will be, as per usual, isentropic compression. So we're going to call that point 1 up to point 2. So that's step 1 to 2, isentropic compression from 100, we'll just call that 100 kPa up to 1 MPa. Okay, and that's P1. T1 is going to be 27 degrees C, which is equal to 300 K. Okay. Next is constant pressure heat addition. So on the PV diagram, constant pressure is going to be a horizontal line over to 3. Okay. This is where our Q in stage is going to happen. And then finally from 3 to 1, P equals CV plus C2. Since that's given as a slope of a line, just one variable, it's going to be linear, so it's not going to have any curvature to it. So we know it's going to be a straight line, as straight as I can draw on an iPad with a crappy stylus, from 3 to 1. Alright, next is going to be our TS diagram. So we're going to start with point 1. We're going to go up from 1 to 2. Since it's isotropic, the change in entropy is going to be 0, so S1 is going to be equal to S2, okay, up at point 2. Next, from 2 to 3 is our constant pressure heat addition. So if constant pressure heat addition, we're going to be increasing temperature, okay, and then our return back to 1. Okay. Again, we have Q coming in, Q going out. Forgot to draw that on this one. Q out's over in this stage, since it's just a 3-stage process. Alright, moving on to the next slide. So that's part A. Part B wants us to find the heat rejected, okay, which is equal to Q out, okay. So remember, E in minus E out equals delta E system. So we're going to have minus Q out minus W out is going to be equal to M U1 minus U3. Okay, so that's happening for process 3 to 1. Rearranging a little bit to make the negatives not be so nasty. Q out is going to be equal to, let's see here, minus W out minus M U1 minus U3. Okay? So this is what we're trying to find. Okay. We were given a mass of 0.004 kg, so we know that. So U1 minus U3, delta U, remember, can be more or less set up as CV delta T. So we can write that as M times CV T1 minus T3. Okay, so we know T1, that's good. CV we know to be 0.718 kilojoules per kilogram Kelvin. Okay, so we don't know T3, so we need to find T3. Okay, and we also need to figure out how to deal with this minus W out. Okay, big W out. We know that big W is equal to mass times little w out. So that gets us one term out of the way. So now we need to find the work out from 3 to 1. Okay? So those are the two things that we need to find. So we know from our, since it was stated that air standard assumptions are applicable and that constant specific heats, we can use the formula T2 over T1 is equal to P2 over P1 times K minus 1 over K. Okay? We know that K is equal to 1.4. We know T1. Okay? Now, do we know T2? We don't know T2. So that would be one variable we're trying to find. We know P1 gave us that. P1 was, where was that at? That 100 kPa and 1000 kPa for P2. So now we know P1, P2, T1, which was 300K, and we know K. Alright, so now we can solve for T2. T2 turns out to be 579.2, okay, which doesn't help us a ton yet, okay, but it's a good start here. Next thing, we know that Qn is equal to MH3 minus H2. This is from process 2 to 3, which we know Qn, which is good. They gave that 2.76. Now, since it's constant specific heats again, we can do MCP T3 minus T2. Now this is the part where T2 comes in handy from before. So now we know Qn M CP, which is 1.005. Okay. And then we know T2 from the previous steps, and now we can solve for T3 using all those numbers, and T3 is going to be equal to 1266K. Okay, so now we know T3. So that gets us a little bit further towards this. So now we have that whole second term. We know all four of those variables in that. Okay. Alright, the last thing we have to find out is that little w from process 3 to 1. Okay, we had before. So we know if we just draw our PV diagram here really small. Go 1, 2, 3. That's kind of cruddy, sorry. That's linear. 3, 1, 2. Okay. So we know that work, since that's linear, is just the area underneath there. Okay. So we can set that up as P3 plus P1 over 2 times V1 minus V3, which using the ideal gas law is just P3 plus P1 over 2 times RT1 over P1 minus RT3 over P3. Okay. So we know P3 is 1,000 plus P1 is 100 all over 2. R we know is 0.287. T1 is 300K over 100 kPa minus sorry, something bumped on my iPad there. Let me see where I left off. Minus 1266 over 1,000. Okay. Plugging all that in, little w is equal to 273.7 kilojoules per kg. Okay, so now I know little w. Now we have everything that we need in order to plug back into that first equation. So Q out, I'll rewrite it again, is equal to minus mass times little w minus mass times CV, T1 minus T3. So now we know T3, T1, CV, mass, little w, m. We can plug everything in and get Q out being equal to 1.679 kilojoules. Okay. Alright. So, the last part, try and squeeze it on the slide here, is wanting us to calculate the thermal efficiency. So N, which in this state is 1, minus Q out over Q in. So N is equal to 1 minus Q out. If we just calculated 1.679 all over Q in, which they gave us 2.76. So our thermal efficiency is going to be 39.2%. Perfect. Well, thanks for tuning in this semester. Hope you learned something, and maybe we'll see you again in heat transfer.